The topic today is colligative properties. Before we continue, I would like to ask you this question. What do you think about this truck? What does it do? What are they using it for? By the end of this lesson, you should be able to answer this question. Another question is, what do you think if we put salt in water and boil it? What do you think will happen? Okay, have these two questions in mind as we continue. By the end of this lesson, you should be able to answer them. Okay, what is colligative properties? Colligative properties are properties of a solution that are different than those of a pure solvent by itself. Okay, these are colligative properties are properties of a solution that are different than those of a pure solvent by itself. These properties are also dependent on the concentration of the solute or number of solute particles, but not their identity. So there are 4 types of colligative properties. There are freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So we look at each of these. What is the meaning of freezing point, boiling point, vapor pressure, osmotic pressure? We look at each of these first. So what is vapor pressure? When we boil water, for example, water vapor evaporates. That vapor pressure exerts some pressure, okay, when the vapor is in equilibrium with the liquid or solid form or both of the same substance, okay? Or we can say vapor pressure is a measure of the tendency of a material to change into gaseous or vapor state, and it increases with temperature. These images can help in the understanding. So you start boiling this, you see these are evaporated. When they evaporate, each of them will be exerting some pressure. Okay, the more the vapor, the more the pressure it exerts. Okay, so the less you see, the less the vapor, the lower the vapor pressure, the more the vapor, the higher the vapor pressure. And here you see the more the evaporation, the higher the vapor pressure. Okay, so that's what vapor pressure is. Okay, when something is more volatile, when like you have ethanol, for example, anything that is more volatile, because more of it to evaporate, it will exert more pressure. Okay, so that's what vapor pressure is. Then boiling point. What is boiling point? Boiling point of a liquid is temperature at which the vapor pressure equals to the external pressure. External pressure is more atmospheric pressure. Okay, look at this. This is atmospheric pressure. This is showing the vapor pressure from whatever is boiling. Okay, so as soon as this equals this, then that's when the boiling takes place. Boiling takes place. So, but we know that the boiling point of water is 100 degrees Celsius, and this is at 1 atmosphere. So the boiling point can vary depending on the location. Okay, we look at that shortly. Okay, if you're in a place where the atmospheric pressure is not 1, obviously the boiling point will be less. So it says the lower the pressure of a gas above a liquid, the lower the temperature at which the liquid will boil. Okay. Then what is freezing point? Freezing point is the temperature at which the liquid changes to a solid. Water freezes at 0 degrees Celsius. Okay. This is a simulation. This is at Mount Where is location? Altitude is this. This is top of Mount Everest. Okay, you're top of Mount Everest and you want to boil something, boil water. Okay, let's start the simulation. Remember, boiling point, for boiling point to take place, the vapor pressure and atmospheric pressure has to be equal. So we have, this is atmospheric pressure, this is the vapor pressure, this is what you are boiling. You see the particles, you see some vapor pressure. So let's go. You see that? You see that? The particles are evaporating. So this vapor will be exerting some pressure. Then atmospheric pressure at Mount Everest is 0.31. Watch. Whoa. As soon as this is equal, then this is the boiling point. See, it stops changing. This is the boiling point. The atmospheric vapor pressure here and the atmospheric pressure are equal. So the boiling point is 69.4. Okay. Now, let's look at a phase change diagram. Let's say we have ice cubes and we apply some heat. Here is solid. Then it will melt. When it's melting at this time, the temperature is not changing. Why? Because you still have ice and water together there. It's not fully liquid, it's not fully solid. That's why this time the temperature is not changing. Any heat applies, keep on changing the ice to liquid. Then when everything changes to liquid, the temperature starts rising again. Look at the particle diagram as solid here. The particles are together, and then the liquid is separated. Now it's liquid, totally liquid. Now you keep on applying the heat. When it evaporates, as it evaporates, it becomes gas. But before it becomes totally gas, you have gas and liquid together. So at this point, that's the boiling point. Okay, the boiling point here, because there's solid, there's liquid and gas together. Okay, it's changing from liquid to gas. So this is the boiling point. When all the liquid changes to gas, then the temperature starts rising again. The reverse, if you have gas changing to liquid, is condensation. Like you have cold water in a cup, all of a sudden you see the cup wet, that's condensation. That means you have air and liquid in both of them are there. That's why the phase change, the temperature is not changing. As soon as all the gas changes to liquid, the temperature will start going down. And then if you keep on reducing the temperature, you keep on changing the temperature, reducing it, decreasing the temperature, like you put it in the freezer, you see now you have ice and liquid together. Ice and, yes, it will be ice and solid together. Now, the temperature will not be changing at this time, there's phase change. Then when everything changes to solid, then that's here, the temperature starts going down again. So that's change. I want you to see this in a simulation that will make more sense. This is not very, very good, but I want you to give you an idea, just an idea, because it just doesn't go all the way to where to what we just saw. So I start solid, okay? You watch what is happening here, you watch what is happening here at the same time. Okay, here we go. The temperature is going up, it's solid. Now you have solid and liquid. You see, the temperature is not changing. As soon as everything disappears, no more ice, it's only liquid, the temperature will be going up. Okay? It will be going up. Still going up. It's going up. Now it doesn't have the capability of going all the way, but at least you have an idea what I mean. Okay, now we can look at it in another. Let's look at this. We have to observe what is happening. Okay, now the temperature is not changing because there's liquid and ice. Now it starts rising because it's totally liquid. It's totally liquid. The temperature is going up. Now, let's see what happens. Everything, you see that? Now there's gas and liquid. You see the temperature is not changing. That's boiling point. So let me do it again. Take note. At melting point, the temperature is not changing. At boiling point, the temperature is not changing. When it's only liquid, the temperature is changing. Just for you to have an idea, at that time that is flat, as we saw in that graph, the phase change diagram, that time is flat. There's no change because every heat added is being used to convert the solid to liquid or is being used to convert all the liquid to gas. Okay, that's phase change. We talked about the four colligative properties, vapor pressure lowering. What does that mean? Okay, this, when heat is applied, this water, there's evaporation, okay? This is pure water. There's water vapor that is up here. Now, when we add salt, when we add solute or salt, what happens? This salt will be hindering the evaporation of the water vapor. Because it's hindering the evaporation of water vapor, there's less water vapor, therefore less vapor pressure. So that's what vapor pressure lowering means. Because of the addition of the solute or addition of the salt will prevent more water vapor from evaporating, therefore less evaporation, less vapor pressure, less water vapor, therefore less vapor pressure. So that's what vapor pressure lowering means. Now, freezing point depression. Pure water will freeze here, but when you add salt, it will hinder the water molecules from forming ice crystals. So that's what freezing point depression is. This salt will hinder the water molecules from coming together to freeze. Therefore, it causes freezing point depression. Then boiling point elevation. Okay, now there's pure solvent. Here there's salt added. Now, remember, boiling point takes place when the boiling atmospheric pressure and the vapor pressure are equal. Now, here, there's less water vapor, less pressure. So it will, you need to apply a lot more heat. It will take longer for vapor pressure to equal the atmospheric pressure. So in the process, it will cause boiling point elevation. So the boiling point will be higher when the salt is added. Let's look at this simulation, boiling point. We'll be looking at heat will be applied here. I think I'll make this smaller, hopefully, so you can see everything. Okay. Now, boiling point, I run the experiment. Okay, here, I run the experiment. Okay, you see that there's heat applied. Look at what is happening here. This is pure water. This is 1 mole of sucrose. This is sucrose. 2 moles of sucrose, 3 moles of sucrose. What is your observation? Look at here. The boiling point is increasing. This is pure water, no particle, no solute, 100 degrees, 0.00 degrees Celsius here. You added 1 mole. You see, the more solute, the more the concentration, the more the boiling point, the boiling point increases. Okay? Let me reset and run that again. Remember, this is being heated, okay? Okay, so that's clear. Let's reset and add, okay, a different type of, the other one was sucrose. This one we add sodium chloride. Remember, this sodium chloride is ionic compound. It will break apart, so you have 2 solids. Okay, sodium ion and chloride ion, okay? Because it will break apart. Look at that. You compare this to the first one, the sucrose, okay? The particles here, there are more particles here. That's why the boiling point is even higher here, because there are more solids, solid particles. So if I do this and I do this, okay? Look at that. There are more solid particles. Look at how it's increasing. Okay, now let's look at freezing. We go to freezing. Okay. 1 particle, 2 particles, 3 particles. You see that? Freezing point depression. You see that? Then reset. What if I do this? Freezing, run. More particles. You see? The more it lowers because the more the particles or more the concentration, the more the effect. The properties are affected, the lower it gets. Then let's do this. We put this one, we run. More particles. You see that? So this is just simulation to show you what is really happening. So you see the particles hinders the molecules from coming together, from freezing. Okay. Before we go to the last colligative property, which is osmotic pressure, we have to understand what osmosis is. Osmosis is the passage of a solvent through a semi-permeable membrane, separating a dilute solution from a more concentrated solution. This is clearly here, semi-permeable membrane, okay? Then this is dilute salt solution, this is concentrated solution. So semi-permeable membrane is a membrane that allows certain types of molecules to pass through it, but prohibits the passage of other types of molecules, okay? Now, we want to also watch a video that explains this better.
Static pressure are 2 different types of fluid pressures which are responsible for allowing the movement of fluid from one location to a different location within some given region of space. Now, let's begin by describing what osmotic pressure is. But before we actually define what osmotic pressure is, we have to discuss something called osmotic potential as well as osmosis. So let's suppose we have the following object, a marker. Now, anytime we take a mass, for example, the marker, and we let go, we know that mass, the marker, will always move from a higher gravitational potential to a lower gravitational potential, so objects naturally move down their gravitational potential gradient from a high potential to a low potential. Now, in the same analogous way, if we take a water molecule, the water molecule will always move down its water potential gradient, also known as the osmotic potential gradient. So water naturally moves from a high osmotic potential to a low osmotic potential. Now, when an object, a mass, is on the ground, we define the ground to be a zero potential. And in the same exact way, we give pure water a value of 0 osmotic potential. So pure water is arbitrarily assigned an osmotic potential of 0. Now, if we take the pure water and now we add some type of additional solute molecule, for example, sodium ions, then we decrease the osmotic potential of that non-pure water. So now it becomes more negative. So pure water is given a potential of 0, but anytime we take pure water and we add our solute molecules, now we're decreasing the osmotic potential, we're making it more negative. Now, let's suppose we have the following system. So we have a closed container as shown. On the left side, we have pure water. On the right side, we have water as well as our additional solute molecules. So these green molecules are solute molecules, for example, our sodium ions. Now, separating the left side from the right side is a semi-permeable membrane. And this semi-permeable membrane has small pores that allows the movement of water molecules, but does not allow the movement of these solute molecules. So the green dots cannot actually move across the semi-permeable membrane, but the water molecules not shown can actually move across the semi-permeable membrane. Now, from this discussion above, we know pure water has a potential, an osmotic potential of 0. But this water that contains the solute molecules has a smaller, a more negative osmotic potential. So we have a high osmotic potential, a low osmotic potential, and what that means is water will begin to naturally move down its osmotic potential gradient from the left side to the right side in the same analogous way that the marker will move down its gravitational potential gradient. So once again, suppose the left side only contains pure water while the right side contains water along with some solute molecules shown in green. The two sides are separated by a semi-permeable membrane that only allows water to move across. Now, since pure water has an osmotic pressure and an osmotic potential of 0, but the right side has a more negative osmotic potential, so a smaller osmotic potential, water will naturally flow from the left side to the right side down the osmotic potential gradient. Now, we can rephrase this. We can say that water moves from a low solute concentration, the left side, to a higher solute concentration, the right side. So this is known as osmosis. So osmosis is the process by which water naturally flows from a high osmotic potential or low solute concentration to a low osmotic potential or a high solute concentration. And this is described by the following diagram. So water tends to move from a high osmotic potential, the left side, which is also the low solute concentration, and it moves to the low osmotic potential or the high solute concentration, the right side. So it always naturally moves from this side to this side, and this is known as osmosis. Osmosis is the process by which water naturally moves down its osmotic potential gradient. Now, the next question is, what exactly is osmotic pressure? Because osmotic pressure has to do with the process of osmosis. So now let's suppose we take the same exact situation and now we place a impermeable membrane, for example, our hand, we place the hand in front of the semi-permeable membrane. So now the hand acts as the impermeable barrier. What will happen next? Well, as the water tries to move across this barrier, because we have an impermeable barrier, our hand, the water will not be able to move across. And that's because our hand, the impermeable barrier, actually creates a pressure that prevents that osmosis from taking place. And that's exactly what osmotic pressure is. Osmotic pressure is the pressure that needs to be applied to actually prevent osmosis from actually taking place. So if we block the semi-permeable membrane with some type of impermeable barrier, for example, our hand, we will be applying a pressure that will ultimately stop osmosis from taking place. So the pressure that must be applied to stop the natural flow of water down its osmotic potential gradient is called osmotic pressure. So notice that the water tries to move this way, but our osmotic pressure points in the opposite direction, because what it does is it ultimately stops the water from actually moving across this membrane. Now, what about hydrostatic pressure?
So osmotic pressure is the pressure that must be applied to prevent the net flow of solvent through a semi-permeable membrane from a solution of lower solute concentration to a solution of higher solute concentration. Okay. Then, here we go. The pressure created by water moving across a membrane due to osmosis. Okay. So this is a video on colligative properties.
Solid particles or ions disrupt the non-covalent solvent-solvent attractions, thereby creating changes in various properties of the pure solvent. For example, if a solute is added to a pure substance, the boiling point is higher and the melting point is lower than that of the pure substance. How much these properties change depend on the concentration of the solute used. Colligative properties are those properties that depend solely on the concentration of the solute used. They depend on the number or amount of solid particles used. They don't depend on the nature or type of particle used. Now, 4 major colligative properties are known: vapor pressure, osmotic pressure, boiling point elevation, and melting point depression. I'm going to briefly talk about the first colligative property, vapor pressure. If you want to go into more detail about vapor pressure, check out my link below. So vapor pressure is simply the pressure due to the gas molecules found in dynamic equilibrium with their liquid molecules. Now we see that adding non-volatile solute decreases vapor pressure according to Raoult's law. Now if you want to learn more about Raoult's law, check out my link below. Now recall that a non-volatile solute is a solute that will not evaporate. So let's see 2 systems. We have 2 systems. The first system is the system before we add our non-volatile solute. The second system is after the addition of the non-volatile solute. Before addition, a certain vapor pressure is created due to the molecules found in the space above. After addition, some of the solid molecules will be replaced by the non-volatile solute, and so less will evaporate, and therefore the vapor pressure will be less. Now adding volatile solute, or molecules that do evaporate, increases vapor pressure, according to a modified version of Raoult's law. And that's simply because now we have the solid molecules evaporating and the volatile solute molecules evaporating. So the final pressure is the sum of the 2 pressures. The second colligative property is called the boiling point. The boiling point is the temperature at which the liquid molecules have enough kinetic energy to escape into the gas state. Now this occurs when the vapor pressure of the liquid equals the atmospheric pressure. So we see that the boiling point is related to the vapor pressure. Adding non-volatile solute lowers vapor pressure, and now a higher temperature is required to raise our vapor pressure to that final atmospheric pressure. So more energy is required. And in fact, we could use a formula to find the change in the boiling point. So change in boiling point is equal to a constant Kb, which is related to the substance being boiled, times the molality, so moles over a kilogram of solvent, times I. I is called Van 't Hoff factor, and this is the number of particles a single solute molecule dissociates into. So, if our solute is sodium chloride, we see that sodium chloride dissociates into exactly 2 particles. So our I in an ideal solution will be 2. In a non-ideal solution, there's something called ion pairing, or the momentary aggregation of ions in a solution. And this will cause I to slightly lower. And that means in an ideal solution, this will be 2. In a non-ideal solution, this will be slightly below 2. The third colligative property is called a freezing point, or the melting point. This is the temperature at which the liquid molecules lose the kinetic energy and cannot sustain the liquid state, and they form a crystalline structure called a solid. Now the freezing or melting point is not related to vapor pressure the same way that boiling points are. By adding a solute or an impurity to a pure substance, we increase entropy and make it difficult to form a crystal structure. Therefore, more energy needs to be taken away from our system. And this means that our freezing and melting point lowers. Now, the amount by which our freezing and melting point lowers can be found by a similar formula. The change in temperature is equal to a new constant that depends on the substance being melted or frozen times the molality of our substance times I, the number of particles a solute dissociates into. Now we have to be careful with freezing point depression, because adding a solute to a pure substance will only decrease the freezing point to a certain extent. Eventually, our solvent will become our impurity, because if we add enough solute, the amount of solute will surpass the amount of solvent. And when that happens, adding any more solute will actually make our freezing point rise and our melting point rise. The fourth colligative property is called osmotic pressure. Osmotic pressure is the tendency of water or some other solvent to flow into an area with a higher solute concentration. Now, to demonstrate osmotic pressure, let's build a system. In this system, we have a cell that's enveloped in a semi-permeable membrane. Now, this membrane allows the flow of water, but it does not allow any solute molecules to pass through. Now, on the outside, we have many more solute molecules than on the inside. So let's see what entropy tells us about such a system. Well, entropy dictates that a system will always strive to even out. And that means in this system, the solute molecules will want to move inside the cell. But remember, because this is a semi-permeable membrane, solute molecules will not be able to go inside. And that means instead, water will try to even out the system. And water will flow from a lower concentration to a higher solute concentration. So we can define osmotic pressure in a second way. Osmotic pressure is the pressure that needs to be applied to a membrane to stop the flow of solvent into an area of a higher solute concentration. So whenever we talk about an ideal solution that has a very low solute concentration, we can find osmotic pressure on one side of the equation or on one side of the membrane by using this formula. And this formula states that osmotic pressure is equal to Van 't Hoff factor, which is the number of particles a single molecule or a single solute molecule breaks into, times molarity of our solution times the gas constant, or R, times temperature in Kelvin. Now, whenever we talk about osmotic pressure, we also talk about osmotic potential. Now, any pure substance, such as pure water, is automatically given an osmotic potential of 0. And any impure substance, so if we add a solute to water, we give it an osmotic potential of less than 0. So it has a negative osmotic potential. And we define the flow of a solvent from a high osmotic potential to a low osmotic potential. So since the outside has many more solute molecules, it has a more negative osmotic potential. And that means water will flow from a lower osmotic potential to a higher osmotic potential, or from the inside to the outside.
Okay, take your time and answer these questions. There are no answers. All the answers are in the video, okay? If you don't understand it, you go back and watch it again so you'll be able to answer this question. Inability to answer this question shows lack of understanding. I think you have enough materials here to be able to answer the question. Thank you for watching.